Question 6 is where we start to introduce Bronsted-Lowry terminology properly into looking at acid and base reactions. So I think it's helpful if we just quickly review what their ideas are about, and then we'll see how they apply in question 6. So the starting point is that they didn't like equations like this, which say, right, HCl is a strong acid, so when it breaks up, it just falls apart like that into H plus and Cl minus. Their view was that anything to do with acids and bases is always more transactional than that. In other words, things don't just fall apart, they get ripped apart by interaction with something else. And in this case, of course, the only other thing around is water. And so they said that the reason that the H plus separates from the Cl minus is not just because it falls apart, but because the proton is donated to a water molecule. And so they rewrote this equation and said, really, the water isn't just passively sitting there encouraging the HCl to fall apart, it's actually reacting with it like this, and giving you Cl minus. But they said the H plus ion doesn't just fall off, it's accepted by the water. And of course the water has got a lone pair. On the oxygen it's got two, but one is enough for it to accept the H plus from there. And so they proposed that that's really what the H plus ion is. It's H plus having been grabbed by a water to form H3O plus, which is sometimes called a hydronium ion. So that's taking a more Bronsted-Lowry approach by saying that HCl is a proton donor, it donates a proton, and if it's going to donate it, something has to accept it, and the proton acceptor, the thing that's doing the accepting, is the water. So this is an acid in the Bronsted-Lowry sense, but water is here acting as a base in the Bronsted-Lowry sense because it accepts a proton. The other thing that they sort of insist on is the idea that these reactions are always, in principle, reversible. Now the equilibrium might, as in this case, lie very far over to the right, so that an overwhelming majority of HCl molecules do break up and form chloride ions and allow H3O plus to form. But it's always an equilibrium. I mean, basically, all reactions are equilibria ultimately. It's just that often when the equilibrium lies so far over to the right that you can basically ignore the backward probability, you think of it as a reversible reaction. But there's no strict dividing line. It basically depends on how negative your delta G is. The more negative delta G is, the further over to the right it will be. So they like the idea that all of these reactions are in principle reversible, even if the probability of going backwards might be almost vanishingly small. And that's important because what it means is that the reverse reaction is going to be an acid-base reaction as well, because the forward reaction is transfer of a proton from HCl to H2O, and so the reverse reaction is just going to be transferring a proton the other way, from H3O plus to Cl minus, to go backwards that way. And of course that means that H3O plus is a proton donor, so it's an acid, because that's what it's doing in the backward reaction, and Cl minus in the backward reaction is accepting a proton, so it's a base. So this is the Bronsted-Lowry version of that, by saying that you have to introduce the water into the equation because otherwise there's no acceptor to pair up with HCl as a donor, and secondly that you have to think of it as a reversible reaction, and that the reverse reaction is also an acid-base reaction. So the idea of conjugate pairs, which is what question 6 is examining, is that a conjugate pair is just a pair of species which differ by an H plus ion. So HCl and Cl minus are a conjugate pair. That's the acid which has the H plus to donate. That's the base which can accept an H plus to go back to there. So the pair are called a conjugate pair, and there's always a conjugate acid, which is the thing that already has the extra H plus, so it's able to donate it and be an acid. The Cl minus is the thing that lacks an H plus, so it can be a base and grab the H+. So that's one conjugate pair, and what Bronsted-Lowry pointed out is that in any acid-base reaction there are always two conjugate pairs, because obviously if this is donating a proton, this must be receiving it, so it's the conjugate base, and it's the conjugate base of H3O+. So H3O+, if we go backwards the other way, acts as an acid and donates a proton, so that too is a conjugate pair. So you just need to get used to analysing acid-base reactions in those terms of two conjugate pairs coming together like that. And it introduces some odd things, because water you've probably always thought of as being neither acid nor base. It's the thing that's kind of the neutral thing in the middle. But what this equation is telling you is that in some circumstances, in the presence of an acid, water can act as a base, and as we'll see later on, in other circumstances, water can act as an acid. So it just changes your perspective slightly. So a conjugate acid-base pair, all you really need to remember is that they just differ by one H+ ion, only ever one H+ ion. So for the first pair, we've got the acid and the base, and it's told us in this case that the base is HSO4-. So you just think, right, a base is a proton acceptor. If that accepts an extra proton, what does it become? And the answer is H2SO4. In the second one, we've got NH4+ down as an acid. So acid is a proton donor. If this donates an if this donates a proton, loses H+, what does it become? And the answer is NH3. So in other words, we would say ammonia is the conjugate base of NH4+, or we could say NH4+ is the conjugate acid of NH3. In the third one, we have C6H5OH, which hopefully you recognise is phenol. C6H5, remember, is a phenyl group. And we learnt in organic chemistry that phenol is a weak acid, so it can be a proton donor. If it donates H+ to something, then it becomes its conjugate base, which is the phenoxide ion, which is that. The fourth one is ethanoate, CH3COO-. So that's a base, therefore it's going to act as a proton acceptor. If you add H+ to it, you get ethanoic acid, and that's the conjugate acid. And nitric acid, sorry, H2NO3+ is the one it gives you. Now this is an interesting one, because if that's an acid, it's going to act as a proton donor, it's going to give H+ away, and you can see if you take H+ away from that you get HNO3. So that seems straightforward enough, but it leads to something really weird, which is that nitric acid has appeared in the base column. And again, that makes the point that often species can act as either an acid or a base. It depends what they react with. So nitric acid normally gives an H+ ion away, and therefore we think of it as an acid, but there's no reason that it can't act as a base. If you look at the structure of nitric acid, it looks like this. Okay, so you've got the H+ there, which can be given away, but you've got lone pairs on these oxygens, and of course there's no reason that one of those can't be given away to form a dative covalent bond to an H+ ion, which is what's happening there. So just because something is called an acid doesn't mean it can't, under certain circumstances, act as a base. And that particular one is actually quite important, because you've come across that, not explicitly, but in reality before. Because remember, in nitration, which is adding NO2 to or rather substituting NO2 into an aromatic ring, remember the conditions are that you make a mixture of nitric acid and sulfuric acid, concentrated acids mixed together. And what actually happens there is that sulfuric acid acts as an acid and gives H plus away, and nitric acid acts as a base to form this. So you get this equation, gives you H2NO3 plus HSO4 minus. But then what happens is you get a second equilibrium, which is that H2NO3 plus can break up to give you H2O plus NO2 plus, which of course is the electrophile that you need for aromatic substitution. So that process by which NO2 plus is generated actually is in part an acid-base reaction in which nitric acid acts as a base, accepts H plus from the sulfuric acid to give you that intermediate species which then breaks down. Apologies, by the way, if you can hear the dog snoring in the background. There he is, showing tremendous interest in everything I have to say. So in question 7 we're comparing ethanoic acid and phenol. And you know from your organic chemistry that both of these are weak bases. But hopefully what you also remember is that this is much weaker than this. And the key evidence for that, if you recall, is that this will react with carbonates and cause fizzing, but this is such a weak acid that it won't react with a weak base like carbonate. So it's asking us to think about that in the context of the conjugate base. So if we write these, and let's just write a simple, we could write a Bronsted-Lowry type thing, but we don't need to for these purposes. So let's just write a simple dissociation equilibrium because it just kind of is easier to see what's going on. So we're comparing really these two reactions. So this in each case is the conjugate acid because it can donate a proton, and this is the conjugate base because it can accept a proton to go back the other way. Okay, so that's the conjugate pair in each case, and ethanoic acid gives you a conjugate base which we call ethanoate, and phenol gives you a conjugate base which you call phenoxide. So it asks us then which of these conjugate bases is the stronger base. So what we're saying is that this is the stronger acid, so in other words this equilibrium lies further over in this direction than this one does. Okay, so more of the ethanoic acid is ionized in aqueous solution than is the case for the phenol. So if you think that in the context of the other direction, it means the backward reaction, phenoxide is better at it than ethanoate is. It's just looking at the same issue from a different perspective. So the fact that this equilibrium is further over to the right, you can either think of as being the acid ethanoic is better than phenol at giving up a proton, or you can think of it from the context of the base and say phenoxide is better at picking up a proton, so pushes the equilibrium that way, better than ethanoate does. So phenoxide is the stronger base in comparison to ethanoate, in the same way that ethanoic acid is the stronger acid. So it's just two different perspectives on really saying the same thing. So question 8 is asking us to do some examples of writing acid-base processes as reversible reactions in this Bronsted-Lowry formulation where you have the two conjugate pairs shown explicitly. So ammonia is a base, which means that it can accept a proton from something, and in this case it's going to accept it from water. So ammonia is the base, because it's going to be the proton acceptor, and water, therefore in this reaction, functions as an acid, because it's going to donate a proton to ammonia. So if this is the conjugate base of ammonia, the conjugate acid is going to be NH4+. Okay, because when it picks up a proton, it becomes NH4+, and that could then function as an acid to donate the proton and go back again, and that's the point about the reversible sign. So water has here functioned as an acid, given up a proton, and of course what it leaves behind is OH-, and as we know, OH- can act as a base, grabbing H+ and going back that way. So that's a reaction that you already knew, because we've already used that equation in the past to explain why aqueous ammonia is alkaline. But now you can see that it fits in very nicely with the Bronsted-Lowry definition. So nitric acid and water, we know that nitric acid gives up protons in water, so it donates a proton, so it goes in the acid column, and water functions as the base, because it picks up the H+ ion from the nitric acid. So the conjugate base is NO3-, which is just what happens when HNO3 loses one proton. The conjugate acid is H3O+, because that's what you get when water picks up the proton from nitric acid. You get the hydronium ion, which is that. And of course that could act as an acid, going back in the other direction to donate a proton back to back to NO3- to recreate HNO3. So between the two you see something quite interesting here, which is that water can act as an acid, donating a proton and leaving OH- behind, but it can also act as a base, accepting a proton and becoming H3O+. So that raises the question, if water can be both an acid and a base, can it sort of react with itself? So if we put two water molecules here, this one is going to act as an acid, which means it's going to donate a proton and become OH-, and it donates the proton to here, so this becomes H3O+. So the interesting question then is, what's the status of that reaction? Because obviously it's a balanced equation, it fits in with the Bronsted-Lowry definitions. We've seen water can act as an acid, it can act as a base, but the question is, does it? Just because we can write an equation doesn't necessarily mean it happens. Well, the evidence comes from the fact that, for example, if you measure the conductivity of pure water, it's very low. Conductivity, remember, arises from ions dissolved in the water, and if this reaction happened a lot, you'd have quite a high conductivity because you'd have all these ions floating around. In reality it's really quite low, which tells you that this equilibrium lies far over in this direction. But it does happen a bit, and this self-ionization of water to make H+ ions, or H3O+, if you write them in the Bronsted-Lowry way, to make these and OH- ions, actually has quite an important role to play in issues to do with pH, which we'll get onto later. So don't get the wrong idea. Just because we can write this equation, it doesn't mean that it completely changes your view of water and you think, oh, water's full of ions. Only something of the order of one water molecule in 50 million or something actually breaks up into ions like this. So it's a very, very, very tiny proportion, but it's not zero. So in water there is a small, very, very small concentration of these ions resulting from one water molecule acting as an acid, donating a proton to another one.